Hello everyone, and a warm welcome to today's session, day one on the bootcamp for Foundation to Electrochemical Cells and Reactions. My name is Abhinav, and I'm currently working as a battery development engineer at Decibels Lab. I'm currently working on model-based design and Simulink modeling of electrochemical cells, especially lithium-ion cells. And I'm also working on battery testing. So where I am currently testing lithium-ion cells in different scenarios and using that data from the cell testing to develop batteries and understand their behavior in different situations, right? So today's session will be about understanding just the basics of what is an electrochemical cell, what are some of the basic reactions that occur in a electrochemical cell, and some examples such as a Daniel cell, a simple Daniel cell, a lead, and some of the reactions which we will see in the Daniel cell. So basically, there are two reactions, the two primary reactions. And also, we will see the same two primary reactions for other types of chemistries, such as lead acid battery, nickel cadmium battery, and nickel metal hydride battery. Yeah. So we will see some of these examples. We will compare some of their properties, and then finally, we will have a brief overview and come to the conclusion of today's session. Okay, so before we get into the the very specific part of reactions as such, let's first have a look at what are the different energy storage devices available in today's energy market. Okay, so briefly, here you can just see four simple examples of what are the different available energy storage devices. Okay, so first and foremost is a flywheel. So basically, a flywheel is a rotary device or a rotary component that can store rotational energy or basically mechanical energy in the form of rotation, right? And whenever needed, the flywheel can be either isolated or engaged, and from then on, the rotational energy can be utilized, in any useful place for producing useful work. Okay, so similarly, we have hydroelectric dams, so where we have water stored at a height, and whenever a demand of energy is there, the dam gates are open and water is allowed to flow from that height. And because of the change in from potential to kinetic energy, some work can be done by either rotating a water turbine or collecting it in another reservoir, where basically smaller turbines can be used to produce power. Okay, so basically it's conversion from potential energy at a height to kinetic energy. And then we also have magnetic energy storage. So basically, magnetic energy storage is possible through large induction coils or transformers, basically. So these large induction coils, they have this ability to store electrical energy in the form of magnetic energy. And whenever needed, the induction coils can be engaged, and the magnetic energy can be converted to the required electrical energy, and it can be utilized for producing useful work. Yeah. And finally, we have electrochemical cells, or basically also called as batteries, which store energy in the form of chemicals, or basically chemical compounds, which can be utilized in the form of chemical reactions to produce electrical work or electrical energy. Okay, so our focus today will be on electrochemical cells. Okay, so where we look at what are the two different types of electrochemical cells and what are the reactions pertaining to electrochemical cells. Okay, so some other examples of energy storage devices could be capacitors. So basically, we have super capacitors or ultra capacitors, which are basically like very large in size, and they can store electrical energy in the form of charge. Okay, and whenever required, it can be discharged, and a large amount of energy can be utilized to produce power. Okay, so we also have compressed air storage. Okay, so this isn't exactly a primary source of power. So compressed air can actually be a secondary or a auxiliary storage unit, where you can store some amount of work has to be produced in order to store air, and later on this air can be released to produce some useful work. Okay, so this compressed air can be stored in an air reservoir, and later on it can be released for some work. Okay, so these are some of the examples of some major energy storage devices. Okay, so as I said, our focus will be on electrochemical cells or batteries. Okay, so proceeding further, so basically, what is an electrochemical cell? Well, it can be simply defined as a device, an energy storing device, and an energy producing device that can basically convert the stored chemical compound energy to electrical energy, or vice versa, electrical energy to chemical energy. Okay, so we will see how exactly this happens in the next few minutes. Okay, so here you can see just some few very common examples of what are the electrochemical cells used in today's market, right? So a lead acid battery. So all types of your common road cars, your trucks, all of them use lead acid batteries. Lithium ion pouch cells, which are used in EVs, lithium ion cylindrical cells, which are also another way of storing lithium ion chemical energy. And also we have Duracell batteries, or simple zinc, nickel zinc type of batteries. Yeah. So there are different types of chemistries and different types of formats available in this market, and depending upon the usage, you can choose whichever one is the best suited for your requirements. Yeah. So we can broadly categorize electrochemical cells into two segments. Okay, one is called as an electrolytic cell, and one is called as a galvanic cell. Okay, so you might have heard of this scientist Luigi Galvani, and he's the one who introduced this type of cell, where it utilizes chemical energy, or basically chemical compounds, to produce some amount of electricity. Okay, and this galvanic cell is basically only one, only unidirectional, as in to say it can only produce electrical energy from chemical. Okay, it cannot do it the other way around. Okay, this is also called as a voltaic cell. So basically it produces electrical energy from the stored chemical energy, and hence it is also called as a primary cell. Okay, so a primary cell is basically a non-rechargeable cell, which can only be used once. Your a very common or a very simple example would be your Duracell battery, or your everyday cell, which is used in your TV remotes or clocks or watches, or simple devices like calculators, blood pressure monitoring instruments, things like those. Yeah, so where your battery basically, or your cell, is not rechargeable, and it only produces a certain limited amount of electrical energy. Okay, and an electrolytic cell, on the other hand, is the exact opposite of a galvanic cell. So here we saw that it produces electrical energy. Here it produces chemical energy from an external electrical source. Okay, so it's basically electrical to chemical. Okay, so if some amount of electrical energy is supplied to this particular device, then chemical reactions start happening, and some chemical compounds or some reactants are obtained, from which further work can be done, such as simple processes like electrolysis of water, or electroplating of gold. Yeah, so we know that there are certain jewelry articles that on which silver or gold, or other type of chemicals are deposited, right? And that is basically done through a process called electrolysis. Okay, so this electrolysis works on this principle of an electrolytic cell, where external electrical source an external electrical source is utilized to produce chemical energy within the device. Okay, so either chemical compounds or some sort of a subproduct can be obtained, or a byproduct can be obtained, which can further be utilized in gold plating, or electrolysis of water, where you can split water into hydrogen and oxygen, and further utilize it for some useful work. Okay, so this is some of the common examples of an electrolytic cell. So these are the two categories, or two segments of an electrochemical cell. Okay, but when you combine them together, okay, when you combine these two concepts together of an electrolytic cell and of a galvanic cell, you get what is called as a secondary cell. Okay, so basically it can work both ways. It can produce electrical energy from the stored chemical energy, and vice versa. It can receive electrical energy from an external source and replenish the chemical energy. Okay, so nowadays, most of the lithium ion cells that you see, or most of your lead acid batteries, your NiCad batteries, all of these batteries are rechargeable and they fall under the category of secondary cells. Okay, so these are the basic classification of an electrochemical cell. Okay, so with that, we'll progress into some basic structure, this basic structure of a electrochemical cell. So what are the main components of this cell? So basically, we have to start with the two of the main components, okay, which contribute to the reactions occurring inside the cell. Okay, so basically they are the anode and the cathode. So your anode can also be taken, an anode is also called as the negative terminal, okay, and your cathode is called the positive terminal. Okay, so here in this structure, you can see in this particular diagram on the left hand side, you can see the cathode is right over here. This is your cathode, okay, and your anode is just on the other side of this. So this is your gray colored segment that you see here. That is your anode, okay, and these two are separated by what is called as a separator layer. Okay, that the main importance of this separator layer is to prevent the anode and cathode from touching each other. Okay, because if they do, there will be a short circuit that occurs within the cell, or basically there will be a rapid flow of electricity or charge within the battery itself. It will not function correctly and it can catch fire or immediately even explode. Okay, so that is your main purpose of a separator. It acts as an insulator and also acts as a isolating material between the cathode and the anode. Okay, so each of these material, I mean to say each of these components, anode and cathode, are specifically made out of something called as active material. Okay, so they are specifically made out of something called as active material. Okay, so what exactly is an active material? Basically, active material is nothing but the constituting chemical compounds, or basically your chemical elements that make up the anode and cathode as per the desired reactions that have to occur within the cell. Okay, and from those active material, the cell is able to produce the required energy. Okay, so there are different types of active material available. Okay, so we will just have a brief look of that when we come to the reaction part. Okay, when we come to the chemical reactions part, we'll take a look at what are the different anode and cathode and electrolyte active materials. Okay, so next, coming to the electrolyte. So basically, electrolyte is a sort of medium. It is a sort of a connecting medium between the anode and the cathode. Basically, through which ions have to flow between the cathode and the anode. Okay, so the reactions that occur within the cell, these reactions actually release some amount of ions. Okay, and these ions flow between the cathode and the anode, and also from the anode to the cathode. So for that purpose, you need a conducting medium, and that conducting medium is the electrolyte. Okay, so the electrolyte basically it does not participate in any of the reactions or has any minimal participation in the reaction, and it only allows, it's basically its function is to allow the ions to flow without any resistance or without any disturbance, without any hindrance. Okay. Then coming to the current collector is basically this large green terminal that you see here. Basically, it is your connecting your connection between your electrolyte and the positive terminal outside the battery here. So this basically allows your electrons to flow from within the cell to the external portion of the cell. Okay, so that's what the function of the current collector is. And then we come to the sealing ring. The sealing ring acts as an isolating instrument. So basically, it has two functions. It should not allow any of the dust or any pollutants from entering inside the cell. And preventing any of the internal components from leaking outside. Yeah. So that is the function of the sealing ring, and also maintains the pressure, the air pressure within the cell. So all electrochemical cells have to function within a certain air pressure. Okay. There are certain standard requirements for the cell to function within designed air pressures. And the sealing rings, one of the most important function is to maintain this air pressure, because this air pressure will directly influence the rate of reaction inside the cell. Okay. And then finally coming to your positive and negative terminal. So as I already pointed out, this is your positive terminal and this will be your negative terminal. Okay. So these are your main components of the entire cell. Okay. So with that, let's progress into the simple example of an electrochemical cell. So what you're seeing here is basically what is called as a Daniel cell. All right. So this Daniel cell is it was introduced by a British scientist in the year 1840. Okay, so this was one of the earliest earliest examples of uh, uh, an electrochemical cell, which basically produces a very small amount of current from the simple sulfates that were present here. So the sulfates act as the electrolyte. Okay, so this portion that you see here, this portion of the cell, this gray and blue portion of the cell, these are your electrolytes. Okay, this is nothing but your conducting medium. And basically these electrolytes are nothing but sulfates or some sort of a salt solution. Okay, so pretty much any cell, not just the Daniel cell itself, but pretty much any electrochemical cell out there usually utilizes salt solution as a medium of conducting ions between the anode and the cathode. Okay, so in this case, your anode will be your zinc. This is your negative electrode. Okay, and your positive electrode is here. This will be your cathode. Okay, so this is how basically this simple cell is constructed. Again, these are your wires from here. These are your constructing wires. So these are your connecting wires. They connect the anode and the cathode. Okay, and this particular instrument you're seeing here, this is just a simple device which is utilizing the chemical energy within the cell. Okay, and your final component here, this would be your salt bridge. Okay, this is called the salt bridge. Okay, so this salt bridge is basically just a chemically neutral and chemically inert component of this cell, which basically only allows the ions to travel from zinc to copper and copper to zinc. Okay, so this is just a connecting equipment. It does not play any role or any part in the reaction. Okay, so you can just see how exactly this particular cell works. So simply, what happens is the zinc element that you see here breaks down into two components. Okay, one is called as the zinc ion. Okay, or also called as cation because it is positive in nature. Okay, and electron. Okay, so your zinc element is split into two components. One is called as the zinc ion, or also called as cation, and two electrons. Okay, so your electrons are the one that travel into the outer circuit or the wires basically over through here. This is how your electrons will transfer from your zinc to the copper. Okay. On the other hand, copper will undergo combination. Okay, where you can see copper ions and the two electrons released in the released from zinc will combine to form copper. Okay, so this is your these are the two primary reactions that occur. Okay, and the first reaction is called oxidation. And your second reaction is called reduction. Okay, so let's take a look at this particular animation once again. So here you can see zinc is split up into electron and a zinc ion, which then gets dissolved into the solution. Okay, this gets dissolved into the solution and is transported through this particular salt bridge to the copper side. Okay, meanwhile, the copper ion released over here then recombines on the zinc side. Okay, so this is how your reaction will be completed, and this is how charge neutrality is maintained. Okay, so in any electrochemical cell, irrespective of what chemistry it is made out of, it has to maintain something called as charge neutrality. Okay, so charge neutrality is very important, because if there's any buildup of ions, or if there is any sort of blockage of flow of ions from one side to the other side, then basically there will be a charge imbalance, and it can cause the cell to stop working, or it can even cause like some dangerous side effects such as short circuiting, or even ignition, spontaneous ignition. Okay, so for that charge neutrality to be maintained, this is why the salt bridge is provided over here. Okay, so your ions are exchanged without any problems. Okay, so this is how a simple electrochemical cell would work. Okay, so your two primary reactions, as I mentioned earlier, this is nothing but your oxidation and reduction. Okay, and usually your oxidation occurs at the anode, and your reduction reaction occurs at the cathode. Okay, so with this reactions in mind, we will then proceed to the few examples. So here you can see a complete workup of the Daniel cell, the complete split up of the reactions. So starting with the zinc as the anode, as I said, zinc is split into zinc ion and 2 electrons. Okay, so the same 2 electrons that is given out over here is going towards the copper cathode, and here your copper sulfate solution or your electrolyte will provide the copper ion, and this copper ion will combine with the electron here to form copper. Okay, so here you can see individual reaction that is provided over here. So each reaction on each side, from the zinc side and from the copper side. Okay, once both the reactions are once the reactions are added together, or when both of them are summed up together, you get something called as the overall reaction. Okay, the one that you see over here written beneath is called the overall reaction. Okay, so with this is basically how the Daniel cell would work. Okay, and basically it's connected to a voltmeter to measure how many electrons is flowing through at any point in time. Okay, so just like that, we can just take a look at some of the other chemistries as well. So we have seen how exactly a simple Daniel cell works. Okay, now we will just take a look at how lead acid cells work. Okay, so lead acid cell, we know that lead acid cells, our lead acid batteries are very commonly used in our modern automobiles today. And basically, why is it called lead acid? Well, it's called lead acid because your anode is made out of lead, and the electrolyte is a particular acid, and that is nothing but a sulfuric acid. Okay, H2SO4. Okay, and your anode will be, which is nothing but your negative electrode, will be lead Pb. Okay, lead, pure lead, and lead oxide will be your cathode. Okay, so which is given by PbO2. Okay, so I had mentioned earlier what are the different active materials. So these are what are your active materials. Basically, they are the materials, or they are the chemical compounds that actively participate in the chemical reactions within the cell. Okay, so different cells make up the complete battery over here, as you can see. So each cell will have this reaction. So I will write down the reaction here. So at the anode, or at the negative electrode, so let's write down here, this is the negative electrode. Okay, at the anode, lead will undergo oxidation, right? So we had seen oxidation occurs at the anode. Okay, so lead Pb will undergo oxidation. So lead will combine with 1/2 of sulfuric acid, because this is only the reaction occurring at the negative electrode. So lead will combine with sulfuric acid to form lead sulfate. Okay, lead sulfate and a hydrogen ion plus an electron is released. Okay, so these are your byproducts, or these are your chemical products. Basically, this portion, this is your products. And these are your reactants. Okay, so these are your reactants. So lead will react with sulfuric acid, 1/2 of the sulfuric acid, to form lead sulfate and release 1 electron. Okay, so this is the reaction occurring at the anode. Okay, I will also write the reaction occurring at the cathode. So at the positive side, okay, so lead oxide undergoes reduction. Okay, so lead oxide PbO2 plus HSO4. Once again, the other half of the sulfuric acid plus the electrons being released in the oxidation reaction plus the hydrogen ion gives, once again, lead sulfate plus water, H2O. Okay, so this is your reaction occurring at the cathode. Okay, so these are the two reactions. So your reduction and your oxidation. Okay, so these are the two primary reactions occurring within the cell. Okay, and if you add these two reactions, you get what is called as the overall reaction. Okay, so let's write that down. So I will write here on the top side. So your overall reaction will be the sum of these two put together. So if you add them, what do you get? You get lead Pb plus lead oxide PbO2 plus H2SO4. Okay, reversible reaction, lead sulfate plus H2O, water. Okay, so this is your overall reaction that I have written over here, which I'll just highlight like this. Okay, so this is your overall reaction, and this is your combined reaction, which is called redox reaction. Okay, so your redox reaction are the two reactions that have to simultaneously occur for the battery to work. Okay, so these are the primary reactions that occur within the lead acid battery. Okay, so now we have seen what are the two different reactions, right? But there are also something called as side reactions. Okay, so apart from your main reactions, there is also something called as a side reaction. Okay, so we will not be going too in depth into that, but there is another influencing factor to how the battery works. It's called side reactions. Okay, so basically side reactions are reactions because of the main reactions, reactions due to reactions. And over time, what happens is that these reactions start to affect the battery's performance, and they start to hinder the battery's ability to produce power. They add more and more resistance to current, and they produce lesser amount of voltage. Okay, you just have to know that side reactions is basically because of the byproducts developed during the main reactions. Okay, so for example, when lead reacts with sulfuric acid, some small amount of byproducts will be released. Okay, and they will start to react with either the electrolyte or with the anode or cathode, and they will start producing more and more amount of byproducts, which can add to reduced performance. Okay, so we will not be going again, as I said, we will not be going too much in depth into the side reactions part. Okay, so these are your main reactions that occur within the lead acid battery. Okay, so along the same lines, we also have a nickel metal hydride. Okay, so which is NiMH. So again, why is it called nickel metal hydride? So basically, a cathode is made out of nickel, and anode is made out of some sort of a hydride or a metal hydride. Okay, so your metal could be aluminum, it could be manganese, it could be magnesium. Okay, Yeah, it could be any one of these metals, depending upon what kind of physical and chemical properties you is desired from the cell, what kind of performance is desired from the cell, whether it should be a high performance or low performance type cell. There are various different factors that have to be considered as to choosing what kind of metal constituent is wanted. Okay, so its reactions are pretty simple. So the anode, which is your metal hydride, will react with uh, one half of the electrolyte. So MH plus hydroxide. Okay. So one half is just the hydroxide ion, OH minus, gives metal plus H2O. Okay. And releases one electron. Okay. So this is your reaction at the anode. So this is your reaction at the anode. Okay. And at the cathode, let me just choose a different color for this. So yeah, so at the cathode, which will be your positive electrode. So here, your nickel oxyhydroxide, which is your cathode, nickel oxyhydroxide, reacts with water. So whatever water is released over here, it will react with water plus one electron, gives nickel dihydroxide. So nickel NiOH twice plus releasing one hydroxide ion. Okay, so this is your complete reaction occurring within the nickel metal hydride cell. Okay, and as I said earlier, if you add the two reactions at the cathode, at the anode, if you add the oxidation and reduction reaction, you will get the complete overall reaction, or also called as a redox reaction, which I'll write over here. So your overall, will be your metal hydride, okay, plus your nickel oxyhydroxide, gives nickel dihydroxide plus metal. Okay, so let's write that down. MH plus nickel oxyhydroxide, reversible reaction. So please keep this in mind that these are all chargeable batteries, rechargeable batteries. So hence the reactions are all rechargeable, gives nickel dihydroxide plus metal. Okay, so if during discharge, it will be towards the right side, and during charging, it will be towards the left hand side. Okay, so the same thing in case of the lead acid battery as well. Towards the right side is discharge, and towards the left is charge. Okay, so these are the reactions pertaining to the nickel metal hydride battery. Okay, so if you want to know about the voltage that is produced because of these reactions, for a lead acid cell, it would be usually around 2 volts. Okay, and for a nickel metal hydride battery, it would be roughly around 1.4 volts. Okay, so this is something which we will look into in the next session, where we'll perform some numericals and we'll understand something called as a reduction potential. And in that, we'll understand how exactly that potential comes from. Okay. So along the same lines as nickel metal hydride, we will also see the same reactions in nickel cadmium. Okay. So instead of metal hydride, we'll just have cadmium. So the same exact reactions, I'll not be writing that now. So whatever you saw for NiMH, your nickel metal hydride, you'll see the same exact reactions for nickel cadmium. Okay. So moving on to lithium ion, probably the most famous example of today's modern cells, modern electrochemical cells. So your anode is made out of graphite, or further, if you look into the structure, it will be actually made out of lithium carbide. Okay, lithium carbide is LiC6. Carbide is C6, 6 atoms of carbon and 1 atom of lithium. Okay, so when oxidation occurs, lithium carbide LiC6 will split into lithium ion, okay, plus electron plus carbide, okay, 1 carbide ion. Okay, so this is your reaction at the anode. So which I will just write down here, anode. Okay, and your reaction occurring at the cathode will be your lithium ion plus electron plus a metal oxide. Okay, so your cathode will be made out of some sort of a metal oxide. Okay, that metal oxide could be either manganese or aluminum or titanium, iron, depending upon what kind of requirements are there, what kind of performance is needed. So it will be nothing but metal oxide plus LiC6 plus electron, which will give lithium metal oxide. Okay, so this is your reaction occurring at the cathode. This is actually a highly simplified version. There is like your metal oxide will actually be replaced by the particular metal element being used. Okay, so if you combine the two, you will get your overall reaction. So let's write down the overall reaction. Okay, so your overall will be LiC6 plus metal oxide, reversible reaction. Always keep in mind that these reactions are always reversible. So lithium metal oxide plus carbide C6. Okay, so this is your overall set of reactions that occur within the cell. Okay, so your lithium ion cell. So of course, in any cell, not just lithium ion cell, the reaction also depends upon how many atoms or how many electrons you're utilizing within the active material. So the more number of electrons, the more number of voltage, the more amount of voltage the cell will produce. Okay, so we know that for lithium ion cells, roughly your average voltage will be somewhere around 3.7 to around 3.6 or 3.7 volts. Yeah. So this is your complete overview on what are the different reactions that occur within the different electrochemical cells. Okay. So now we have seen all of the different chemical reactions that occur within the cell or within the different cells. So now let's have a final comparison, between all of these different chemistries. So, it's important to understand why exactly lithium ion cells are used. Yeah. So the two of the most important parameters that define as to why lithium ion cells are used, it's because of the first two parameters. It's because of what is called as energy density, how much chemical energy a particular cell can store and release at a given moment with respect to its volume. Okay, with respect to the amount of chemical compounds stored, in terms of liters, how much energy it can store. Okay, so you can see here in terms of lead acid or nickel cadmium, these are all low energy density, hence low power applications. You don't see them, you'll not be able to see them powering like extremely powerful gadgets or devices like EVs or scooters or electric cars as such. But you can see that lithium ion is most preferred in that case simply because of this number here, 250 to 600 watt-hours per liter. This is a very huge advantage over all other cells. Coming to this last one, nickel zinc, you can see that it says 240 watt-hours per liter. Yeah, but that is only because of the amount of heavy amount of modifications done to the internal chemistry of this particular cell. But by nature, nickel zinc cannot provide 240 watt-hours continuously. It will only provide it initially, and after which it will drop down to like a very low value, even below nickel cadmium. Yeah. So same thing with specific energy as well. So similar to energy density, this is with respect to the amount of energy stored per unit mass of the chemical constituents. Okay. So again, you can see that it has a vast advantage over the other types of chemistries. And efficiency, your overall operational efficiency, in terms of charging, discharging, is very high, 95%, while it is low for lead acid batteries and for all other chemistries as well. Again, as I said, nickel zinc will only come close to 80% to a certain amount of time if nickel zinc batteries are charged very fast. Okay, they have to be charged or they have to be operated at a very high current rate in order to be sustained at 80% efficiency, but that's not always the case. Yeah, but you can notice consistent 95% as an average, overall for lithium ion cells. Also coming to something called a self-discharge. So basically, if you consider a cell that is being stored in a particular environment, in a particular condition for a very long period of time, say for example, over a period of 8 months or 12 months or more than 12 months, something like 36 months. Yeah. So what happens is cells or batteries usually tend to start losing some amount of energy permanently. Okay. And that is what is self-discharge. And for lithium ion cells, it is again the least. Again, that is because of the chemical properties within the cell. Cycle life, basically how many times they can be charged and discharged, up to 3,000 times, up in today's figures, up to 3,000 to 5,000 times. While you can see lead acid batteries have to be replaced like every now and then, like every 2-3 years or so, or as such. Yeah. And it is the lowest in terms of nickel batteries. And finally, coming to nominal voltage, basically this is actually a direct result of having a very high energy density. So higher your energy density, higher your nominal voltage. Okay, so you can see 3.8. Depending upon what chemistry you're using here in the lithium-ion cell, based on that you can have like extremely high voltage. So 3.8 is actually the highest that has ever been achieved from lithium-ion. And as I said, 2 for lead acid and 1.5, 1.4 to 1.5 for nickel batteries. Okay, so this is a brief overview as to why exactly lithium-ion cells are preferred. In today's EV applications, your electric cars, electric buses, even electric trains, and now even they're looking at more advanced and modified lithium-ion cells for electric aircrafts. So yeah, these are the this is the complete highlight as to why lithium-ion cells are used. Okay. So coming to our last topic for today, what exactly are the advantages and disadvantages for lithium-ion cell? So your advantage right away is that they have a very high energy density and very high nominal voltage. So that actually allows you to, get more range out of your for your electric vehicle. So nowadays we know that in the market, more amount of range, as in to say upwards of 2,000 to 3,000 kilometers is the current demand, right, on one single charge. So that is only possible if you use lithium-ion cells, and that is exactly because of its high energy density and high nominal voltage. Yeah. Also, low self-discharge. So as I said, it does not lose much energy over time. But on the disadvantage, it is that high chances of cell ignition. So we know we have seen many reports in modern days that their Ola S1 Pro or your Okinawa scooters, all of these they can suddenly catch fire, right? So that is because of your extremely volatile electrolyte. Okay, it's because your electrolyte is extremely volatile, which means even a little bit, even if it's exposed to a little bit excessive temperature, right? Or even if a little bit of electrolyte starts to leak out from the cell, it can instantaneously catch fire. Okay, it can even explode. So for that purpose, even lithium-ion cells currently are still, pose a major threat. Okay. So one other major problem is dendrites. So one good example would be your Samsung Galaxy Note 7. So because of dendrites, internal short circuits can form, and this kind of dendritic formation is very, very, it can form at a very high rate within the lithium-ion cells. Yeah. And another, in terms of manufacturing and processing, cobalt is used. So cobalt actually has to be used within lithium-ion cells, and cobalt is extremely expensive to process and to mine, to manufacture, to transport, because cobalt is actually a rare earth element. It is not commonly available, right? So it has to be like taken from very deep portion of the earth. So for that purpose, like lithium-ion cells are generally a little bit expensive compared to your other types of batteries in the market. Okay, and the last one is limited life cycle, due to the fact that lithium-ion cells can age pretty fast. Okay, they undergo something called as aging. Okay, so where your internal components start to wear out pretty quickly. So even though I did mention that there was around 3,000 to 5,000 cycles available, if it starts to age rapidly, say for example, if it's subjected to like high temperatures or a large amount of current rates, then it can actually limit the amount of cycle life for a cell. Okay. So yeah, this is your brief overview of what is the properties of lithium-ion cells. Okay, so that's it for today's webinar. I Yes, so this we have come to an end for today's webinar and today's content. So now we can have a brief session on question and answers. So we can spare about 10 to 15 minutes for that.